Hello everyone, my name is Bassem and I'm a senior research scientist at Hewlett-Packard Labs, and I'll be speaking to you today about energy efficient integrated photonics for next generation computing. So with the advent of artificial intelligence, we have a number of smart devices that are all running different variations of artificial intelligence algorithms, such as autonomous driving or cloud and edge computing, devices such as Amazon Alexa, or programs such as ChatGPT, or even Face ID on the Apple iPhone, are all executing these sorts of deep learning algorithms. And so the number of programs that actually use these deep learning algorithms have actually doubled around every 3.5 months, which is much faster than Moore's law. And as this as the amount of programs are increasing, the demand on compute performance is also increasing rapidly. And also, to be able to perform these algorithms at a higher accuracy, it also requires more compute power. Now with that, these computing systems are executing more operations per second and at a higher power, but also the energy cost and the financial cost of these computing systems is increasing rapidly too. For example, OpenAI trained its GPT-3 model with over 45 terabytes of data, and it was trained over 34 days. It costed nearly $5 million. The energy usage was estimated to be about 936 megawatt hours. And with that, it also produced about 500 tons of carbon dioxide emissions, which is nearly 10 times as much as a car consumes in its entire lifetime. So we really need to start thinking about how we can make our computing systems a lot more energy efficient to run these algorithms. So when you consider these AI algorithms, they're typically run on accelerators such as CPUs and GPUs that are not actually very well suited to run these sorts of distributed, massively parallel neural networks. A large reason for that is due to the von Neumann architecture. So within the von Neumann architecture, there exists a von Neumann bottleneck, which basically is a bottleneck between your memory and your processor and the amount of information or data that could be sent in between the two, as well as the memory wall, which basically tells us that the CPU performance is typically running a lot higher than the memory performance, and so you still have a bottleneck from your memory. And then on top of that, you have a large power consumption that comes from data movement in between each operation. So within the neural network, you have MAC operations or multiply accumulate operations that are executed, and within or between each operation, data has to move from the processor to the memory, and in each cycle of data movement, energy is consumed, which comes mostly from charging and discharging of metal wires. And so really most of the energy is lost in this data movement. So when we want to think about how we can rebuild these systems to be able to run these sorts of neural networks more efficiently. So what better place to get inspiration than the human brain, which is actually considered to be the world's most energy efficient computer. It's estimated to execute about an exaflop of data using only 20 watts of power, which is about 6 orders of magnitude less than what the Frontier supercomputer consumes in order to run an exaflop of data. And so when we consider these sorts of computing systems, such as the human brain, we really have to consider how we can build future computing systems to replicate or mimic the human brain. And so then comes the advent of neuromorphic computing. And in neuromorphic computing, we want to also discover what the most ideal hardware platform to be able to run a neuromorphic computing system is. So one can argue that silicon photonics can actually provide an excellent platform for neuromorphic computing, due to its ability to move data at really high bandwidth and low energy, and as well as its ability to calculate linear operations very well. So due to wavelength division multiplexing, data can actually be transferred and computed on in a massively parallel manner. And the optical signals experience much lower attenuation and generate much less heat than a metal wire does. And then now with the existence of silicon photonics and the market driving silicon photonics, we can really think about scaling these systems a lot higher. And so when we want to consider about how to build a photonic neuromorphic computer, we have to think about all the devices that are required to do so. So when you look at a neural network and you more specifically look at a neuron or an artificial neuron, you typically require inputs, weights, linear summation, as well as a nonlinear activation function. And actually, at Hewlett-Packard Labs, we've developed a 3.5 on silicon photonic platform that can actually provide all of these devices. So one of the key devices required for photonic neural networks are the weights, which are typically implemented in the form of phase shifters, with the most common being thermo-optic phase shifters. However, thermo-optic phase shifters can consume quite a bit of power, milliwatts of power typically, and can be slow in switching speed. So researchers have begun to look at MEMS phase shifters, which are a lot more energy efficient, though they can be quite slow as well and still prone to mechanical failure. So more recently, there has been a lot of research on non-volatile phase shifters such as phase change materials and ferroelectric phase shifters such as barium titanate. However, those materials can still be quite slow in their switching, and with phase change materials, requires about still milliwatts of power to change the phase from crystalline to amorphous. And barium titanate can require a large device footprint. And so when you think about building more dense, scalable photonic neural networks that can be trained, we really need to think about a high-speed, low-power, and compact photonic phase shifter. And so at Hewlett-Packard Labs, we actually have a history of phase shifters. Actually, the MOSFET was actually first developed and invented by Muhammad Atallah, who was actually an engineer who founded or co-founded Hewlett-Packard Labs. And later in Hewlett-Packard Labs, the first memristor was demonstrated. Then the first heterogeneous MOS capacitor was demonstrated within Hewlett-Packard Labs, borrowing the same concept as the MOS capacitor developed by Muhammad Atallah and his MOSFET invention. Those MOS capacitors were then engineered within different types of photonic devices such as microring modulators and lasers, and then later memristors were also engineered within microring lasers and modulators and Mach-Zehnder interferometers, which we will go into as well. So if we take a look at the heterogeneous MOSCAP phase shifter, we actually can save a lot of power in comparison to a thermal or carrier injection type of phase shifter, nearly a 1 billion time improvement. We can actually tune the wavelength, the resonant wavelength of a microring resonator about 1.6 nanometers with only about a picowatt of power. And this is largely due to it being a capacitor and the leakage current of the capacitor being really low, and less than a picoamp. And so also what's nice about these devices is that they're very convenient in integrating them to other types of heterogeneous devices on the same platform. And they don't have any thermal crosstalk, so you can actually bring them closer together and in a more compact integration without any thermal crosstalk to affect the system. They also can be switched at really high speed. We've actually measured about 28 gigabits per second from these devices. So the next thing we developed was the memresonator, which was essentially bringing non-volatile memory directly onto our platform. And so in doing this, we can actually build non-volatile phase shifters, which really require zero power consumption in order to change or to hold a state once it's been switched. So the way that this works is we have on the left here, you can see a microring resonator with a 3-5 sitting on top of silicon, sandwiching a thin layer of alumina oxide. And this can actually be switched by applying a high electric field across of this device. And when you apply a high enough electric field, you actually can cause a conductive filament to form within this oxide material, which then basically reduces the resistance of this device. And so you could switch this device actually from a low resistance to a high resistance state and also back to a low resistance state again, essentially by applying a high electric field in one direction and then in the other direction to switch it back. And so you could see when you switch from a high resistance state to a low resistance state, the device essentially changes from acting as a carrier accumulation type of phase shifter to being like a carrier injection type of phase shifter. So when we measured these devices, we actually were able to demonstrate about 12 hours of retention time, as well as 1,000 cycles switching the device into multiple resistance states. And with each corresponding resistance state, there is a phase shift associated with it. So on the bottom, you could see the change in the resistance within the memristor. And then on the top, you have the corresponding phase shift or wavelength shift in the microring resonator with each resistance state. We also were able to measure the switching speed and energy of these devices by using short voltage pulses to switch the device. So in this case, we used a 300 picosecond 5-volt amplitude voltage pulse in order to switch the device. And we were able to reset the device using a 4.5 volt 900 picosecond voltage pulse. And in doing this, we actually can measure a set energy of about 0.15 picojoules and a reset energy of about 0.36 picojoules, which shows that these are photonic weights that are really low energy and very high speed, which can be used for training within neural networks. We also implemented these memristors on Mach-Zehnder interferometers, and we've been able to again measure about 24 hours of retention time between a low resistance state and a high resistance state and its corresponding phase shift. And when we compare this device to the photonic weight implementations in silicon photonics, such as phase change materials, MEMS, and others, we see that our device is able to achieve a much higher switching speed than most devices available, and a lower switching energy than most devices available as well. Another neat thing about this device is that it can actually be used to monitor the optical power within a waveguide non-invasively, meaning that it will not absorb any of that light. Essentially, by connecting a lock-in amplifier to the device, you can measure the change in conductance that's associated with the device due to free carriers that are generated from defect and surface state absorption of photons. And with that absorption of photons, there is a change in the waveguide conductance. So what's nice about this is it's a temperature insensitive system, though it does require a lock-in amplifier circuit. So we have ways of trying to integrate those sorts of circuits in a more compact way. though it is quite important and useful to be able to monitor the power and the waveguide within a photonic neural network. So this device does find itself a lot of use. So lastly, within a neural network, you need a nonlinear activation function, and with photonics this has been done either with OEO neurons, meaning optoelectronic neurons, which convert from the optical domain to the electronic domain and back to the optical domain. And these neurons are nice because they're robust and they're well developed. However, they do consume power to convert from the optical to the electronic domain. And so there are all optical neurons which can mitigate some of those energy losses. And so here we've actually demonstrated a nonlinear activation function using a quantum dot APD, which injects photocurrent directly to a quantum dot DFB laser on our platform. And so this can actually provide a near ideal ReLU transfer function. And what's nice about this is it's a broadband input, meaning it can receive light over a broad band of wavelengths and be able to run within a neural network. And what another nice advantage is that the APD and laser are fabricated in the same process, so this can be all implemented all on the same chip. Another way of implementing the nonlinear activation function is using an all optical injection locked laser. So in this case we have a quantum dot microring laser which we've injected with an external tunable laser. And when there's enough light injected at a specific wavelength, then we are actually able to excite secondary modes within the slave microring laser. And the power in those secondary modes is actually nonlinear in relation to the input optical power. So when you look at the transfer function of those excited secondary modes, again, in relation to the amount of input optical power, you get something like a sigmoid type of activation function. So this can also be used within photonic neural networks and can avoid the cost of optical to electronic conversion. Lastly, we have now demonstrated or have put together a type of photonic neural network on our platform that we've called the tensorized optical neural network. And so essentially we're able to represent a very large weight matrix with a small photonic circuit or MZI mesh using tensor train decomposition. So the tensor train decomposition algorithm essentially is a way to compress over parametrized neural networks. And so in doing that, you could reduce the number of MZIs that are needed to represent a large weight matrix. And so, for example, to represent a 1024 by 1024 optical neural network, we can do that using 79 times less number of MZIs than you would typically need in a optical neural network. And so in doing this, we could actually build systems that are much more energy efficient than electronic and other types of photonic neural networks that have been already demonstrated in the past. Due to our 3.5 on silicon photonic device platform, which is quite energy efficient, we can actually demonstrate a throughput per unit area energy efficiency that's about 10 to the 4th times better than digital electronics and analog electronics, and about 10 to the 2 better than silicon photonic and phase change material based technologies. So in summary, we demonstrated an energy efficient 3.5 on silicon photonic platform, which is well suited for neuromorphic computing and non-von Neumann type of photonic accelerators. With that, I'd like to thank my team, Hewlett Packard Labs, and thanks